So NIRCam is one of 4 of JW's instruments, and it has observing modes spanning the near-infrared, sort of from 0.6 to 5 microns. Really, that's enabled by this broad range of filters in NIRCam, around 29 filters, and that helps us do things like wide field imaging across the full 2.2 arc-minute field of view, coronography, wide field slitless Grism spectroscopy. And then really what's going to be the focus, I would say, or like an underlying focus of the mode that we're going to discuss today, is this time series monitoring. Now, you can obviously do that in imaging, but really for some of the most interesting applications, you can use Grism time series, where we make use of the long wavelength Grism so far from 2.4 to 5 micron to access exoplanet transits or variability. And now the real change is that we have this short wavelength Grism capability. Before we could do short wavelength photometry, and now we can do spectroscopy simultaneously to the long wavelength that is available for cycle 4. So what does Grism time series look like? Well, we disperse some spectra on the detector. We have a few different choices based on the underlying filter that we apply to the Grism. And that gives us different wavelength coverage that we can use to access different science. So here's an example for exoplanet science, particularly transits. We're going to get this spectrum here at the top for this one's the F322W2. And then in the short wavelength, we're also getting this photometry at the same time. We can extract light curves from this high time sampling and then measure the atmosphere and learn something about its conditions and properties. So the picture so far, I would say from cycle 1 to cycle 3, is that we've made use of this dichroic that's in NIRCam to take short wavelength and long wavelength channel observations. So in the long wavelength, you're using the dedicated Grisms and one of these paired filters to extract the data that you're interested in. And then in the short wavelength, you've probably made use of this weak lens with one of these filters here to obtain photometric time series at the same time. Now, in cycle 4, we're enabling the short wavelength Grism time series, which makes use of this interesting DHS mode and enables a few different filters underlying that, so that really you don't have to change anything to some degree with the setup of the long wavelength, but you can enable this short wavelength spectroscopy at the same time. So what does that look like in a science sense? Here's an example for probably one of the heaviest use cases of Grism time series, which is transmission spectroscopy. And you can see that means if you picked some filter, let's say 322W2 or 444W, you can start to probe these atmospheric features. Here we have the atmospheric spectrum of WASP-39b, the ERS target. So maybe we're sampling things like carbon dioxide, sulfur dioxide, or this water band. But now with the Grism time series, you could also simultaneously sample maybe these sodium and potassium features down here, or with the F150W2, some water features. And then there's a kind of similar story for another application, brown dwarf variability. This is a recent paper that showed with NIRSpec Prism the variability of WISE 1049b. And you can see here that really there's a lot of different variability happening in the atmosphere. And whereas NIRSpec Prism samples at a relatively low resolution, these short wavelength capabilities might be an opportunity to use one of these longer wavelength band passes at higher resolution and still capture some of the variability that's happening in the shorter near-infrared wavelengths. Okay, so with that in mind, how is this sort of enabled? So DHS is kind of an interesting mode. It produces these 10 separate spectra on the detector through these 10 different apertures that align with the telescope mirror like this. And you can see they're all kind of well separated, and they don't really cover the whole surface of the mirror. Really, with the coverage we're getting, if you added up all of these together, would only be sort of 25%. So there's kind of some implicit throughput loss when you're using this mode. And that will come back later as we sort of discuss how this really affects what the spectra look like on the detector and how we handle extracting the spectra. Okay, so just some some basics. The DHS PSFs, they're quite broad. The line spread function is around 10 to 20 NIRCam's short wavelength pixels, so you can kind of compare that to the full width half maximum of the PSFs, which is around 2 pixels. And the dispersion and the resolving power we kind of get is in this sort of 300 to 600 range. So a little bit higher than what you might get from the Spectroscopy. And particularly the first order is where you're going to get most of your information. You will get a little bit from the second order. And you can see that here in this plot. So this is the throughput. You can see clearly the first order really has this dominant throughput. You're not going to get all of this wavelength coverage at once because you're going to have to apply some filter to your observation. But you will get the second order at the same time, and particularly around sort of 0.9 microns, we think that the throughput is higher for the second order, so you're probably going to get better signal to noise there. But this region here, this 0.8 micron region is a little uncertain, and it's hopefully going to improve through cycle 3 calibration programs, which we'll kind of discuss much towards the end of the talk. So what does this look like? You have these 10 different apertures, and if you look at the detector, it kind of disperses them in a sort of interesting way. You have them all dispersed sort of in the same direction across the 4 NIRCam short wavelength detectors. And there are 2 that fall really close to the detector gap, particularly one you can't even see because it's within the detector gap. That would be DHS1. And then DHS6 falls quite close to the detector gap, and that one actually doesn't get used for science. There's no option to extract that spectrum. So that's just a highlight of that there. And then simultaneously to these observations, as I kind of emphasized already, we are obtaining the long wavelength spectrum at the same time on the long wavelength detector. So these are being extracted at the same time. Now, one thing to keep in mind with these observations is that contamination is a little more likely for the DHS. So here's an example of how that might work. Some nearby contaminating source might have its spectra dispersed in a sort of similar space as your science target. And in this case, we might have some like intermediate level of contamination. You know, maybe you could do a good job of still extracting each individual spectra here. But there would be some contamination to deal with. But there's also kind of a variable effect here, depending on the V3PA. If we look at some other situations, you know, where if you have a favorable V3PA, well, there would be almost no contamination at all for the same source at the same position. Or we can look at an example where it's sort of maximum contamination, where really they kind of line up perfectly, and we would lose some wavelength coverage really due to that contamination. This is quite a complicated effect and is something that we're still looking at. Generally speaking, we know that sources at roughly 8 arcsecond intervals in the cross dispersion axis are candidates for this. With considering further developments to XOCTK to produce some sort of contamination model this in time for cycle 5, so not cycle 4. Maybe that will work in a similar manner to the nearest source contamination tool that maybe some of you are familiar with. But at the moment, it currently falls under the shared risk aspects of short wavelength Grism time series. Now, this is the first time I've kind of mentioned this shared risk. This will come up a few times. This mode is new. We're still calibrating it, and there's things to do to really lock down our understanding of the mode and how best to use it. So within that, there will be a couple of points in the talk where we'll emphasize this shared risk and what that really means as a proposer. So in this case, it might mean if you had a lot of contamination, then there might not be a necessary recourse to repeat an observation to get rid of that contamination or pick a more favorable V3PA. That said, you are still welcome to reach out to the people at Space Telescope for support in these kinds of questions to kind of see if we can do some preliminary estimates to kind of make sure the observations work. Okay, so with that in mind, we'll come back to sort of what the DHS looks like, and I'll do a quick mention on the readout. Now, we have a lot of spectra here, right? We have 8 spectra that we're going to attempt to read out across 4 different short wavelength detectors, as well as the long wavelength that we're reading out on the long wavelength detector. And really, that's a lot of detector footprint. Even if we are efficient and we just chop out the region we care about, there's a lot of sort of dead space. So because of that, a lot of work's been put in to design this new multi-stripe readout mode. And that essentially gives us the option to alternatively read and skip rows across the detector. So you'll see this a little bit later, but that's a good thing to keep in mind, that the readout for these spectra is going to be a little bit different to what you might be familiar with from the other modes. Another important thing to keep in mind is that the wavelength coverage of your short wavelength observation is dictated by the choice of your long wavelength filter. So to break that down for you, these sort of 2 to 3 micron filters that you can use with the Grism, they typically disperse the spectra to the left. So because of that, the reference point to start the dispersion is further to the right of the detector. Now, if you're observing with the 444 in particular, that predominantly disperses the spectrum to the right. So because of that, the reference point on the detector is different. It's shifted to the left, and that disperses the spectrum in a different direction. Now, the reference point of the short wavelength filter is explicitly tied to the reference point of your long wavelength choice. Okay, so what that means is the dispersion of your spectrum on the detector is going to change depending on this choice. And here's a kind of pictograph of this. So if you just look at the top plot for now, this 322W2 field point, which is shared for those other 2 and 3 micron filters, you'll see that depending on the short wavelength detector we pick, short wavelength filter we pick, we get different wavelength coverage across different regions of the detector. And we have different coverage of the first and second orders respectively. Now, you can see we have the detector gap here, so sometimes we lose a bit of coverage due to that, and sometimes the spectra butt up against the edge of the detector, so we lose a bit of coverage there. And this dotted line is that reference point I mentioned from the previous slide. So really, if you now switch your perspective and you move to the 444, where we know the reference point has shifted, this dotted line has shifted to the left, all of these spectra that you would get would naturally be translated as well. So your wavelength coverage is going to change as well. You can see an example of that here for the 150W2. Our wavelength coverage at the shortest wavelengths has expanded a little bit to 1.01. It's been truncated a little bit on the left hand side to sort of 1.9, and the detector gap has shifted a little bit as well. And the same is true for the other filters and their own wavelength coverages. So it's just something to keep in mind when you're prepping your observation, that really you want to kind of tie both of these together to get the wavelength coverage you need. Oh, and as a quick mention, this plot and a table describing these wavelength ranges on JDocs currently excludes the 150W, which is also available. That's planned to be updated. But for now, I think it's relatively safe to say that maybe the 150W2 would be a better choice. But there are some cases, maybe if the signal to noise is too high, you might want to drop down to this filter instead. And again, you can reach out if you need clarification on this filter. Okay, so we're reading out the short wavelength and the long wavelength mode at the same time. And there's a lot of spectra we could read out, but we don't necessarily have to read out all of them. There are actually a couple of different options. We can choose to collect either 2, 4, or 8 of the spectra, and we can specifically pick the DHS spectra that give us the best signal to noise to do this. So in the case where we're picking 2, we use DHS 4 and 7, which give us the best footprint on the mirror. If we use 4, then we add the next 2 best. And if we use 8, then we get all of these. And then 1 and 6, if you remember, these are the ones that lie either in the detector gap or close to the detector gap. So those are never read out and aren't accessible for science observation. So what does that look like? Well, it might be a little bit counterintuitive to what you expect. Because we're picking the apertures based on their signal to noise and not their position on the detector, the readout can change a little bit. So in this case, you know, the 2 sub-apertures, we read out DHS 7, which is just at the top of these bottom 2 detectors, and we read DHS 4 with about 36 rows per substripe. So this is a little bit different to what you might be familiar with for the long wavelength, which I think typically has at least 64 rows subarray. For the 4 subapertures, our number of rows goes up a little bit, and we start to add in DHS2 and DHS8. And then for the 8, we can add in all 4 additional DHS subarrays. But we also have 2 options here. You can choose to read out 39 rows per substripe or 63 rows per substripe. Now, this raises an interesting question, and it might be in some of your heads, is how is the detector reading this out? How is it jumping between things? And the main thing to keep in mind is that the DHS spectra are read out separately, but exposed simultaneously. So I'm going to do a bit of a walkthrough here, step by step. And you can imagine this for a case where we're reading out 4 stripes, which is the most you'll ever be reading out on one detector. And in this case, we're using sort of 3 groups in our readout. Now, at the start of any integration, we have to perform a reset of the detector to set the levels back to 0. And what you'll see is that for the first stripe, as the readout moves up to that first stripe, it performs the reset. It then takes some time before it moves to the next stripe, and the reset shifts a little bit in time compared to its nominal position. And then it repeats that for the 3rd stripe, repeats that for the 4th stripe. So the reset is different, and we're starting these exposures at different times, but we are starting the exposure in a sort of shared framework. So if we were to start reading up the ramp, if this is our nominal ramp, we can imagine, okay, we'll go back to stripe 1 after we've performed our reset of stripe 4, and we'll take a read. And then after this, we'll move to stripe 2, we'll take a read of stripe 2, and you'll see there's a difference in the time here, and that's what we call T-stripe, and you might see on some of the tables I've shown or will show. And then we repeat this for stripe 3 and stripe 4. So we've stepped through and we're performing a read on each spectrum, but slightly different times. Now we can jump to our next read. In this case, it's a skipped read. So the detector isn't explicitly recorded to memory, but the read is performed. And a similar thing happens, right? We shift on a time T stripe as we move down across the stripes. And that difference between these reads is still T frame. This is our frame time, which you'll be familiar with from other observations, but this is shared across each of these stripes, right? It's not like one stripe gets exposed more and one stripe gets exposed less, but the T frame is dictated by T stripe, right? So in this case, we have multiple stripes before we can perform another read, so this gets a little bit larger. If you only were reading out 2 stripes, this would be a little bit shorter. And if we keep moving up, we can see T group as well. So in this case, same as T frame, the group time is not changing across each of these stripes. But if we move up, we can complete our ramp for this readout. And you can see we've got 4 sort of duplicates of this ramp, just at slightly different times. And they all share the same total integration time, but they've been effectively broadened by the fact that we're trying to read 4 of them instead of just 1. So you can see a sort of summary here where we've finished our integration and we can start with the next read and continue on. The main caveat I think to keep in mind, which for many people I think might not be too relevant, but is the short wavelength spectra explicitly are not read out at identical times. The difference is around 0.2 to 1.4 seconds between the readouts, depending on how many stripes you're using. But if you're trying to drill down into some really sort of short time variability signal, then you would need to exercise a little bit of caution in how you extract your spectra and how you compare them against each other. So as a sort of pictorial example of that, we're extracting these 8 spectra across the 2 detectors. And, our frame 1, frame 2, frame 3, the signal to noise slowly improves. But the important thing to keep in mind, and I've already mentioned, but, the variations you see here are not because one spectra gets exposed more or less than the other. They all get exposed the same, but those variations are due to the sort of just relative throughputs of each individual DHS element. So I mentioned earlier, that we're reading out short wavelength and long wavelength simultaneously, and the readout of short wavelength really does impact how the long wavelength spectrum is read out. And this is something that's really important to keep in mind for your observations. So to give you another example, on the left, we have the short wavelength example that I mentioned earlier. And on the right, we have the long wavelength. And the way the long wavelength works is that anytime a stripe is read out on the short wavelength, the long wavelength is read out with the same stripe, like the subarray size, but it just repeats it. It doesn't move across the detector. It just keeps doing that over and over. So here's an example here. We start with stripe 1, we perform a reset, and we go down, we've performed 4 resets. What happens to the long wavelength is we actually have 4 resets happen. Everything that gets performed on one stripe to all 4 stripes get repeated 4 times on the long wavelength. So you can see that for the ramp as well. You know, we have this T stripe on the short wavelength between each stripe readout. And then the long wavelength equivalent is we've just taken 4 reads in a row that are T stripe apart. And then if we continue, you know, with the whole ramp, the same sort of pattern happens. We get our skipped reads, our kept reads throughout the ramp, and every time it's sort of in a batch of 4. But the important thing is, you know, that T group, T frame, T integration for the long wavelength is also shared with the short wavelength. Now, this could be an important consideration, and we'll touch on this later, is that because you want to read out these 4 stripes, your frame time is probably a little bit longer than you might normally have for a typical long wavelength observation. So what that means is, you know, we've got so many more reads up the ramp, it's much easier to saturate long wavelength and bump into issues with sort of the wavelength coverage and the sort of constraints you want to obtain. Here's another example, sort of pictograph. You know, we have our one long wavelength spectrum. We're just reading it out over and over. We're not moving around the detector, and just the signal to noise slowly improves as we move up the ramp. So as a bit of a summary on this background information, the first important thing is really your choice of long wavelength Grism filter is going to modify your wavelength coverage of the short wavelength. It's something you want to keep in mind. You can choose whether to read out 2, 4, or 8 of the short wavelength Grism spectra. And I know 8 sounds great, it will give you the best signal to noise, but there is some balancing act you have to do against saturating the long wavelength, because you're going to get that longer ramp, and data excess, which I'm going to touch on in just a minute. The long wavelength has to share the subarray of the short wavelength Grism. So what that means is you're more likely to saturate the long wavelength spectra. You know, the size of the subgrism 64 is smaller than the size of 2 short wavelength Grism subarrays added together. So you're always going to be reading out more pixels. And then when you're using the short wavelength Grism, more detectors are being read out. So you're getting a lot more data, you're saving a lot more data to disk, and you're going to get this data excess.